All right, the beginning of this assignment, we're just supposed to sketch each angle in standard position. So for each of these, you should draw a little X and Y axis. The initial side is always on, starting at the origin, the initial ray is always on the positive X axis. Estimate where 60 degrees would be, something like that. For part B, 180 degrees. Vertex at the origin, initial side positive x-axis. 180 is a straight angle like this, rotates that way. You need to show the rotation direction arrow. Otherwise, there's no way to know if you just sketched a positive or a negative angle or if it goes around more than once. 270 degrees. Origin, positive for the initial side. 270 is all the way down at the bottom of the circle. If you're not familiar with some of these, then you need to figure out each quadrant is 90 degrees, right? So 0, 90, 180, 270, 360. That's where these are coming from. Negative 120 degrees. So you can think about where 120 degrees would be, right? Positive would be in quadrant 2. So you're just doing the opposite of that. So negative 180 would be all the way down here. Negative 120 would have a terminal side, something like that. And again, show your rotation. This one's in the negative direction. Last couple here, negative 450. So both of these angles are more than one full rotation. So I need to figure out how much more so that I can do the, so that I can figure out how far to put the terminal side in. So negative 450, I'm going to add 360 to that. So let's see, break out my skills here. 45 minus 36 is what, 90? Negative 90 degrees, right? So this is coterminal to negative 90 degrees. So when I sketch this, I have to show the correct number of rotations. This is going to look like negative 90 degrees, which would be down here. This is negative 90, but I do a full circle. So there's negative 360 plus an extra 90 degrees in the negative direction. So again, you have to show the direction arrow that it rotates more than once. 600 degrees, now that's not two full circles because 720 is two full circles. So we need to subtract 360, again, to see where the terminal side should fall. So let's see, this would be 240 degrees, I believe. Yeah, positive. So I'm really going to sketch where the terminal side would be if it were 240 degrees. So that's past 180, short of 270. So it's like somewhere about here. I need to show a full positive rotation. So here's positive 360 plus an extra 240. All right, the next section is finding coterminal angles. So it says determine two coterminal angles in degree measure, one positive and one negative for each angle. So just like we did in our notes. 44A, they've sketched the angle for us. To find a positive, I can add 360. So that gives me 474 degrees. So there's a positive. And then I can subtract minus 360. This is a negative, so let's see. I like to line these up here. 60 minus 14 is what? 46. So 246. So there's one positive and one negative coterminal angle. And for the next one, negative 390. So here's an angle that's already bigger than a full circle. So if I could subtract 360, but if I add 360, I still get a negative 30 degrees. So that is one negative coterminal angle. And I like to do that just because I think the math is easier. And then if I want to find a positive coterminal angle, use the 30 degrees because that's coterminal, and then add another 360 onto that. Or another way to think of this is I'm basically adding 720 to get to a positive angle. But I just like this. Negative 30 plus 360 is positive 330 degrees. So there's one negative and one positive coterminal angle. It's not wrong to subtract 360 and get negative 750 or whatever it would be. That's fine too. There are infinitely many correct answers. For 45, we've got negative 300 degrees. So if I add 360 to that, I get positive 60 degrees. There's a positive coterminal. And if I subtract 360, I get negative 660. So that gives me one positive, one negative. And for 230 degrees, I'm going to add 360. It doesn't matter what order you do this in. That's 590 degrees. And if I subtract 360, I get negative, I always have to line it up for my subtraction, negative 130. Don't feel bad about having to do all this little basic math off to the side. It's when we don't write it down that we usually screw it up. Okay, 46. We're still doing the same thing for 46. Okay, so 46 is 445. That's more than 360. So let's subtract 360 instead of adding it. So 445 minus 360. So let's see. 45 to get me down to 400, and then an extra 40 to get me to 360. So that's 85 degrees. There's a positive coterminal angle. And then from 85, subtract 360. So from 85, if I subtract 360, so that's going to give me 35 minus 8 is 27. 10 minus 5 is 5. And negative. Make sure you write the negative sign. Negative 740. Now, I know that negative 720 is 2 full circles. So I'm just going to, instead of plus 360, I'm going to add 720. That gets me to negative 20 degrees. So there's one possible coterminal angle that's negative. And then I can take that and add don't need to add 720. I could. I'm just going to add 360 to that, and I'll get 340. There are infinitely many answers. Add or subtract any number of 360s to any of my answers, and they would be equivalent. So I prefer to stay as close to the angle as I can, within 360 if I can, but that's not required. Okay, 48. So now the directions, I don't have them on the paper, but now the directions are to convert into radians. So 60 degrees, we're going to say times pi over 180. And we reduce. 60 over 180 is 1/3. So we write this as negative pi over 3. 144 times pi over 180. I can divide by 2. When in doubt, just divide by 2 if they're even. Now it's 72 over 90. I can divide both of those by 9, right? I get 8 times pi over 10. I guess I could have done more than 9. If I divide 8 and 10, I get 4 pi over 5. So it's okay if you don't think of the largest number to begin with. These aren't going to be outrageously large numbers that you would be dividing a million times if you just do it kind of slowly. Times pi over 180. So get the zeros out of there, divide by 10. 33 and 18 are divisible by 3. That's negative 11 pi over 6, which is as far as that goes. 10 degrees times pi over 180. Divide by 10, and you get pi over 18. So these are all the radian measure versions of those angles. So these are equivalent. One's in degrees, one's in radians. It's like saying I'm going to measure something in feet and then I'm going to convert it to inches or something like that. Now we go the other way. So we multiply by 180 over pi. So the pi's cancel. Don't do 7 times 180. Reduce here first. So 12 and 180 I can reduce by 4. Remember, 180 divided by 4 was not 90. Wow. 180 divided by 4 was 45. 45 does divide by 3. So I do need to do negative 7 times 15. I'm going to write that down here. And remember, if that messes you up, especially if you're trying to do things in your head, it's the same as 70 plus 35. That's 105. I do that all the time, trying to break things up and figure out what they're going to be. Next one's times 180 over pi. Pi's cancel. 180 over 4 is 45. 5 times 45. Again, you can break this up or you can do this the normal way. It's like times 5, you do 25. 5 times 4 is 20. 22, that's 225. Times 180 over pi. Like I said, you're going to get used to 180 over 4 is 45. 7 times 45 is 35. 7 times 5 is 35. 7 times 4 is 28, plus 3 is 31, so 315 degrees. This next one's negative 4 pi over 3 times 180 over pi. Pi's cancel. 180 over 3 is 60. 60 times negative 4 is negative 240 degrees. All right, let's see. The next set of problems say we're using our arc length formula. So we're given 3 meters and the central angle is 150. I don't think I put this in my video notes, but for this formula, theta equals S divided by R, theta has to be in radians only. So the first thing to do is convert the central angle into radians by doing times pi over 180. 15 over 8 simplifies by 3. We get 5 pi over 6. All right, so we know that, we know that R is 3 meters. So we're going to say 5 pi over 6 times R is going to equal S. I can reduce that 5 pi over 2. And the label would be meters because S is a distance. And you can type that into the calculator to approximate it. I have, from what I did earlier, that it's 7.854. Next one, we're given R and theta. Theta is already in radians. So S, again, is equal to R times theta. That's just me rearranging the original, solving for S. So S is equal to 9 times pi over 3. 9 over 3 reduces to 3 pi feet. Just because there's a pi in it doesn't mean it's automatically radians. 3 pi is an actual number. It's approximately 9.425 feet. We're just leaving it in its exact form. Now this time we have R and we have S, and we're asked to find theta. So theta is equal to S divided by R. So theta is equal to 10 feet divided by 22 feet. If they were in different measurements, we would need to convert first. So 10 over 22, or I would reduce that to 5 over 11. And you don't have to label it, but theta is automatically measured in radians. We don't put a pi on there. Pi is not the label. It's just 5 divided by 11. So if you want to label it, you write out the word radians. Same thing with 94. These are both in kilometers. So theta is just 154 divided by 80. 154, does that divide? I don't think that divides by 4. It divides by 2. 77. And 80 divided by 2 is 40. I think that's as far as that's going to go. Okay. For 96, we're given S and we're given theta, and now we want R. So if theta equals S divided by R, and r theta equals s, r equals s divided by theta. R is equal to 3 meters divided by 4 pi over 3. We're not going to leave our answer complex like that. We're going to say that's the same as times 3 over 4 pi. That's 9 over 4 pi. And R has to be measured in whatever S is measured in, which is meters. Okay, this one, 8 inches, 330 degrees. So again, we would need to convert this. It's pi over 180. So 33 over 18 means that theta is 11 pi over 6. R is equal to S divided by theta. So 8 divided by 11 pi over 6, which is 8 times 6 over 11 pi. 11 doesn't reduce with 8 or 6, so that's 48 over 11 pi. And my answer is in inches for the radius because that's what the arc length was measured in. Last two problems are kind of like the applications in our notes. So remember, linear speed. Linear speed is really just the arc length divided by whatever period of time they're looking at. Okay, so the picture's kind of weird for this one. A satellite in a circular orbit 1,250 kilometers above the Earth makes one complete revolution every 110 minutes. What is the linear speed? So, okay, here's Earth. Doop. And above the Earth, 1,250 kilometers is the satellite, and it's rotating a full rotation around. That's at a rate of 110. Oh, wait, sorry. That took one revolution, took 110 minutes. Assume that the Earth is a sphere with this radius. So, okay, I have not drawn this to scale, but we have this radius here, 6,378 kilometers. All of this is kilometers. Okay, so what are we trying to figure out? Well, what we're really trying to figure out, because arc length is depending on from the center out here, what is the arc length that this traveled in 110 minutes? If I could figure that out, then I'll be good. I'll have the speed, right? What is the arc length? Well, remember, arc length is radius times theta. We're talking about one full revolution, so I know theta is 2 pi. What about r? Well, the radius is this whole thing. So if I add these numbers up, which again I've done ahead of time, I got, give myself more space here, 7,628. So this is the arc length. And then I'm going to pop this into my calculator to see what it comes out to. R is measured in kilometers. So whatever this comes out to, we're going to get kilometers per minute. So that was 7,628 times 2 pi divided by 110. So we're going to round to three places. 435.710 kilometers per minute. That's our linear speed, just about. Okay, next problem, mechanical engineering. The circular blade on a saw has a diameter of 7.25 inches. Right away, I'm going to change that to a radius of 7.25 divided by 2, which is 3.625 inches. And it rotates 4,800 revolutions per minute. Find the angular speed in radians per minute. Well, we almost have it. They give us right now angular speed. They give us the angular speed in revolutions per minute. So it's 4,800 revolutions, full circles. We just have to multiply that by how many radians in a full circle? 2 pi divided by 1 minute. So let's see, 4,800 times 2 pi. So that's about, I guess I could have left it exact, but 30,159.289. That would be radians per minute. Okay, part B says find the linear speed, so in inches per minute, as they contact the wood being cut. Okay, so the linear speed, remember, that's the arc length divided by the 1 minute we're talking about. Remember, arc length, S, is R times theta. So we have R, 3.625. We have theta in radians. It's got to be radians. So that was, actually, I want to leave the exact answer, sorry. So instead of this rounded answer, I'm going to leave this as 4,800 times 2 pi. Or what would that be? What's 48 times 2? 96. 9,600 pi. That's fine. And then it's divided by 1 minute because it's this many revolutions per minute. So we're just figuring this out. All right, so this is 4,800 times 2 pi. So I just need to multiply this by 3.625. And we get 109,327, 109,327.424. And because I hate to round off that little 3, I'm just going to write it down. 4243. And what is this measured in? Linear speed is arc length. Arc length matches radius. Radius was inches per minute. All right. That's it for today's assignment. Please come into office hours if you need help with any of the stuff that we've been learning so far.